Today we are going to discuss about the Drude model on the basis of the free electron gas in metals or free electrons in crystals. While we are discussing the structural aspect of any solids, we have to come into account the effects that is arising due to the electrons in the crystals. As far as we know, we assume that the electrons surrounding the nucleus of an atom are tightly bound. This is valid for insulators, but not for semiconductors and metals. In order to understand the properties of semiconductors and particularly of metals, it is essential to take into account the behavior of electrons in them. So in this study, we shall concentrate mainly on the nature of existence and the role of electrons in deciding the properties of metals. The important or the astonishing properties, okay, uh, of metals are their high electrical and thermal conductivities, high sigma and high K. Soon after the discovery of electron by J.J. Thomson, a number of investigators, particularly Drude and Lorentz, attempted to explain these properties on the basis of the free electron model. For that purpose, they made certain basic assumptions which are listed below, which are the well-known Drude assumption, basic assumptions of the Drude model, I would say. So what basically Drude suggested that in metals, uh, he has applied the kinetic theory of gases and considered them as the gas of electrons or the electron gas. From kinetic theory, it treats the molecules of a gas as identical solid spheres which move in a straight line until they collide with one another. So the time taken by a single collision is assumed to be negligible, and except for the force coming momentarily into play during each collision, no other forces are assumed to act between the particles. Okay, so these are the important assumptions he made, that a metal crystal consists of positive metal ions whose valence electrons are free to move between the ions as if they constitute an electron gas. The second one is the crystal is then held together by electrostatic forces of attraction between the positively charged ions and the negatively charged electron gas. The third one is the mutual repulsion between the electron is ignored. The fourth one, the potential field due to positive ions is completely uniform so that the electrons can move from place to place in the crystal without any change of their energy. And last, they collide occasionally with the atoms, and at any given temperature their velocities could be determined according to the classical Maxwell-Boltzmann distribution law. So on the focus of this model assumptions, the free electron model was successful in explaining the properties such as electrical and thermal conductivities, thermionic emissions, thermoelectric and galvanomagnetic effects, etc. However, this model failed to explain the properties of solids which are determined by their internal structure. It was unable to explain even the observed facts that why some solids are conductors and some are insulators. The first success was achieved by 1927 when Pauli applied quantum statistics to explain weak paramagnetism in alkali metals. In the next year, Sommerfeld published a modified free electron theory by replacing the classical statistics of Maxwell-Boltzmann by Fermi-Dirac statistics. The Sommerfeld free electron theory of metals could be better described as the statistical thermodynamical behavior of a gas obeying Fermi-Dirac statistics. So, beginning with the Drude model, let's focus on the picture above, where Drude assumed that the compensating positive charge was attached to much heavier particles, which he considered to be immobile. Okay, so in this discussion of the Drude model, however, he shall simply assume that when atoms of a metallic element are brought together to form a metal, the valence electrons become detached and wander freely through the metal, while the metallic ions remain intact and play the role of the immobile positive particles in Drude's theory. So this is the basic model he assumed. A single isolated atom of the metallic element has a nucleus of charge E times J okay, this nucleus, where Za is the atomic number and E is the magnitude of the electronic charge, which is 1.6 into 10 to the power minus 19 coulomb. So surrounding this nucleus, there are Za number of electrons of total charge minus E times Za. A few of these Z are the relatively weakly bound valence electrons, capital Z. So the remaining Za minus Z electrons are relatively tightly bound to the nucleus. When these isolated atoms condense to form a metal, the core electrons remain bound to the nucleus to form the metallic ion, but the valence electrons are allowed to wander far away from their parent atoms. So in the metallic context, they are called conduction electrons. Okay, these Za minus Z electrons, what they are relatively tightly bound to the nucleus, they play very less role in chemical reactions and thus are known as the core electrons. So two types of electrons are evolved out. One is core electron and another is conduction electrons. So Drude applied kinetic theory to this gas of conduction electrons of mass m, which move against the background of heavy immobile ions. So the density of the electron gas can be calculated as follows. Density of the electron gas. A metallic element generally contains Avogadro number 0.6 into 10 to the power 24 atoms per mole and rho m by A moles per cc, where rho m is the mass density and A is the atomic mass of the element. Since each atom contributes Z electrons, the number of electrons per cubic centimeter is small n, that is the number density is n by p, is small n is equals to 0.62 into 10 to the power 24 times Z rho m by A. This table typically shows the free electron densities of selected metallic elements such as sodium, copper, silver, gold, etc. where all n are calculated in the units of 10 to the power 22 conduction electrons per cc. Okay, so and used measure of the electronic density rho s, sorry rs, this rs defined as the radius of a sphere whose volume is equal to the volume per conduction electron. Thus V by n is the inverse of the number density, that is 4/3 pi rs cube. From this equation, rs turns out to be 3 by 4 pi n to the power 1/3. This rs can be calculated for each metallic elements. So from this, we can discuss the DC electrical conductivity of a metal. So according to the Ohm's law, the current I flowing in a wire is proportional to the potential drop V along the wire by V is equals to IR, where R is the resistance of the wire, which depends on its dimensions but is independent of the size of the current or the potential drop. The Drude model accounts for this behavior and provides an estimate of the size of the resistance. One can eliminate the dependence of R on the shape of the wire by introducing a quantity which is the characteristic only of the metal of which the wire is composed. That is resistivity, rho, right? So this rho is defined to be the proportionality constant between the electric field E at a point in the metal and the current density J by E is equals to rho J. Where the current density J is a vector parallel to the flow of charge whose magnitude is the amount of charge per unit time crossing a unit area perpendicular to the flow. Thus, if a uniform current I flows through a wire of length L and cross-sectional area capital A, the current density will be I upon A, and since the potential drop along the wire will be V is equals to E times L, this equation gives V is equals to I rho L by A, and hence R is equals to rho L by A. If small n electrons per unit volume all move with velocity V, right? So as I mentioned, if n electrons per unit volume all move with velocity p, then the current density they give rise to will be parallel to v. Furthermore, in a time dt, the electrons will advance by a distance v dt in the direction of v, so that n v dt times a electrons, right, will cross an area A perpendicular to the direction of flow. Since each electron carries a charge minus E, the charge crossing A in the time dt will be minus NeV times A dt. And hence the current density J is simply minus NeV. At any point in a metal, electrons are always moving in a variety of directions with a variety of thermal energies. The net current density is this given by this equation, where V is the average electronic velocity. In the absence of the electric field, electrons are as likely to be moving in any one direction as in any other. So V averages to 0 because all directions are equally possible. So V averages to 0. And as expected, there is no net electric current density. So in the presence of the electric field E, however, there will be a mean electronic velocity directed opposite to the field, that is the electronic charge being negative, which we can compute as follows. So consider a typical electron at time 0. Let t be the time elapsed since its last collision. So its velocity at time 0 will be its velocity v0 immediately after that collision plus the additional velocity minus e t by m it has subsequently acquired. So since we assume that an electron emerges from a collision in a random direction, there will be no contribution from V0 to the average electronic velocity, which must therefore be given entirely by the average minus EET by M. However, the average of the T is the relaxation time tau. Therefore, V average is equals to nothing but EET by M, where J is M E square tau by M times E. So this result is usually stated in terms of the inverse of the resistivity, and the conductivity sigma, as we all know, is the inverse of resistivity. So we come to the point form of Ohm's law, that is J equals to sigma times E, where sigma is nothing but N E square tau upon M. So this can be proved from the Drude model. This establishes the linear dependence of J on E. So J is proportional to E and gives an estimate of the conductivity sigma in terms of the quantities that are all known except for the relaxation time, tau. So we may therefore use this equation and the observed resistivities to estimate the size of the relaxation time. So tau can be calculated by m by rho n e square. From this we can calculate the relaxation times. The typical electrical resistivities of selected elements one can calculate at various temperatures. At room temperature, the resistivity is roughly linear in capital T, but it falls away much more steeply as low temperatures are reached. Okay, that we will discuss later on. Estimate that room temperature resistivities are typically of the order of micro ohm centimeter, that is micro ohm centimeter, or in atomic units of the order of 10 to the power minus 18 stat ohm centimeter. If rho mu is the resistivity in micro ohm centimeters, then a convenient way of expressing the relaxation time implied by rho is equals to 0.22 by rho mu Rs by A0 cube into 10 to the power minus 14 second. So regarding the electrical conductivity in metals, one can know the electron drift in the electrical field, right? So according to the free electron theory, electrons move freely in a conductor. In absence of an electric field, the electron gas is in an equilibrium state described by equilibrium distribution functions, that is the Fermi-Dirac distribution function for a degenerate electron gas, and the Maxwell-Boltzmann distribution function for non-degenerate electron gas. Because of the fact that in a conductor, the number of electrons moving in opposite directions is always the same, their average velocity in any direction is zero, and consequently the distribution functions are symmetric about the axis of coordinates. This explains the fact that in the absence of an external electric field, there is no electric current in a conductor, no matter how many free electrons it contains. So when an electric field is applied to a conductor, the random motion of the electron gets modified in such a way that they drift slowly in a direction opposite to that of the field, and an average drift velocity Vd. As a result, the distribution functions experience a change. In order to calculate the drift velocity, let us consider a free electron in an electric field capital E. It will experience a force EE, which accelerates the electron according to Newton's second law of motion as EE by force per unit mass, where E is the electronic charge, M is the electronic mass respectively. It appears that the electrons should be accelerated indefinitely and their velocity should grow continuously as a result of the electric field. However, this is not correct. In fact, during their motion, the electrons collide with the phonons, impurities, and lattice imperfections. As a result, they regularly lose their kinetic energy and hence the velocity they gained in the field. In other words, the electrons have to surmount a reaction force Fr during their motion through the lattice. The reaction force is proportional to the drift velocity Vd and is directed against it. This is basically 1 upon tau times mvt. Tau is called the relaxation time. Taking into account these two equations, one is Fr and another is acceleration, the equation of directional motion of the electron in the lattice may be written as mass times acceleration, that is the inertial force, equates this force minus mvd upon tau. So this is the basic differential equation one has to solve for the directional motion of the electron in the lattice. This equation tells us that the velocity of the directional motion of the electrons will rise and they will be accelerated until the two forces on the right hand side become equal, when the resultant force acting on the electron, and accordingly the acceleration will become zero, and consequently Vd becomes E tau upon m. Since an electron has a negative charge, it drifts in the direction opposite to that of the field. Okay, electron drifts in this from this. From the expression of the drift velocity of it, since an electron has a negative charge, it drifts opposite in the direction opposite to that of the field, electric field. So in a chemically pure and structurally perfect crystal, where the resistance force approaches zero, even a small field is enough to accelerate the electron indefinitely, so that its velocity grows continuously, which could become infinitely high. Actually, in a perfect lattice, electron wave propagates in an optically transparent medium. One can estimate the relaxation time and the mean free path, but for the sake of the completeness of our syllabus here, we just mention another two important examples. We cannot deduce it, but we know that uh, a current flowing through the conductor with the density, right, is nothing but I is equals to capital N E tau, N squared tau by M times E. It can be remembered as I equals to sigma E. But the conductivity sigma is given by N E squared tau upon M, that is N E mu, where mu is nothing but E tau by M is called the carrier mobility and is defined as the average drift velocity per unit electric field. That is mu is equals to drift velocity per electric field, that is E tau by M. And the resistivity is given by M upon N squared tau. So these two equations, the sigma and the rho, can be easily understood as follows. We expect the charge transported in the medium to be proportional to the charge density n equals to capital N times E. The factor E by M enters because the acceleration in a given electric field is proportional to E and inversely proportional to M. And the time tau describes the time during which the field acts on the carrier. So this equation is of fundamental importance. The electrical conductivity sigma depends on two factors: the number n of the carriers, one is n of the carriers per unit volume, and their mobility mu. The dependence of these quantities, particularly on temperature, provides the basic understanding of the electrical properties of materials. For example, in metals, n is constant and mu varies relatively slowly with temperature. In semiconductors, the exponential dependence of n is of primary importance, while in some insulators, it is the exponential dependence of mu on temperature that is significant while n is constant. So an understanding of the relative contributions of small n and mu enables us to explain the whole spectrum of values of sigma. Let us now discuss the Wiedemann-Franz-Lorentz law. The electrons are not only the agencies of electrical conduction in an electric field, but also responsible for the transport of the thermal energy in a solid. So for this reason, we would be natural to expect a relationship between the two conductivities. One is thermal conductivity, another is electrical conductivity. So the ratio, if we calculate the ratio between thermal over electrical conductivity, comes out to be the ratio of this kind of quantity, pi square k square by 3 e square times t. The relationship was first experimentally established by Weidemann and Franz, and then theoretically explained by L. Lorentz for metals. Weidemann and Franz observed that the ratio Ke by sigma remains constant for all metals at a fixed temperature. However, this was modified by Lorentz, who observed that it is Ke by sigma is a function of temperature is equals to pi square by 3 times e square k square by e square is equals to L. This term L, whose value can be calculated at 2.45 times 10 to the power minus 8 watt ohm degree to the power minus 2, and this is known as the Lorentz number. The experimental Lorentz numbers for some metals can be estimated for 0 degree and 100 degree. It is roughly about 2.31 to 2.61. For silver, it is 2.35. For tin, it is 3.04. For zinc, it is 2.31. Like that, it is at 0 degree, and at 100 degree, this becomes L into 10 to the power minus 8 watt ohm per degree square, roughly 2.37 to 3.20. So they are found to agree with the theoretical value at low temperatures where T is far far smaller than theta d. Lorentz number tends to decrease because the collision time involved in two conductivities is not identical.